Around 4 billion years ago, the early solar system resembled a game of space rock dodgeball, as massive asteroids and comets, and, later, smaller rocks and galactic debris pummeled the Moon and other infant terrestrial bodies. Now MIT scientists have found that the porosity of the Moon's crust, reaching well beneath the surface, can reveal a great deal about the Moon's history of bombardment. In a study appearing in Nature Geoscience, the team has shown through simulations that, early on in the bombardment period, the Moon was highly porous, almost one-third as porous as pumice. But surprisingly, the team found that nearly all the Moon's porosity formed rapidly with these massive IMAPCTS, and that the continued onslaught by smaller impactors actually compacted its surface. These later, smaller impacts acted instead to squeeze and compact some of the Moon's existing cracks and faults. From their simulations, the researchers also estimated that the Moon experienced double the number of impacts as can be seen on the surface. This estimate is lower than what others have assumed. That matters because that limits the total material that impactors like asteroids and comets brought to the Moon and terrestrial bodies, and gives constraints on the formation and evolution of planets throughout the solar system. The study's lead author is EAPS postdoc Ya-Wei Huang, along with C. We know the Moon was so bombarded that what we see on the surface is no longer a record of every impact the Moon has ever had, because at some point, impacts were erasing previous impacts, Soderblom says. What we're finding is that the way impacts created porosity in the crust is not destroyed, and that can give us a better constraint on the total number of impacts that the Moon was subject to. To trace the evolution of the Moon's porosity, the team looked to measurements taken by NASA's Gravity-R. Researchers have converted the mission's gravity maps into detailed maps of the density of the Moon's underlying crust. From these density maps, scientists have also been able to map the current-day porosity throughout the lunar crust. These maps show that regions surrounding the youngest craters are highly porous, while less porous regions surround older craters. Crater chronology. In their new study, Huang, Soderblom and their colleagues looked to simulate how the Moon's porosity changed as it was bombarded with first large and then smaller impacts. They included in their simulation the age, size, and location of the 77 largest craters on the Moon's surface, along with Grail-derived estimates of each crater's current-day porosity. The simulation includes all known basins, from the oldest to the youngest impact basins on the Moon, and span ages between 4.3 billion and 3.8 billion years old. For their simulations, the team used the youngest craters with the highest current-day porosity as a starting point to represent the Moon's initial porosity in the early stages of the lunar heavy bombardment. They reasoned that older craters that formed in the early stages would have started out highly porous but would have been exposed to further impacts over time that compacted and reduced their initial porosity. In contrast, younger craters, though they formed later on, would have experienced fewer if any subsequent impacts. Their underlying porosity would then be more representative of the Moon's initial conditions. We use the youngest basin that we have on the Moon, that hasn't been subject to too many impacts, and use that as a way to start as initial conditions, Huang explains. We then use an equation to tune the number of impacts needed to get from that initial porosity to the more compacted, present-day porosity of the oldest basins. The team studied the 77 craters in chronological order, based on their previously determined ages. For each crater, The team modeled the amount by which the underlying porosity changed compared to the initial porosity represented by the youngest crater. These simulations showed a clear trend. At the start of the lunar heavy bombardment, 4.3 billion years ago, the crust was highly porous, about 20%. By comparison, the porosity of pumice is about 60 to 80%. Thanks for watching. Please subscribe my channel for more videos.